Hi everyone, my name is Haley Fausey. I'm a postdoc at Baylor University. And today I'm going to talk to you for just a minute about gamma ray bursts. So gamma ray bursts are excellent probes of the high redshift universe. They've been seen out to a redshift of 9.4, and their afterglows have relatively simple power law spectra, which makes them great for probing, among other things, the chemical evolution of the universe and the epoch of reionization. And so I want to look at exploring photometric redshift estimation for gamma ray bursts with the high latitude time domain survey for the Roman telescope. So it has a cadence of 5 days. And so what we would be looking for is the Lyman alpha drop-off. So that is a key feature in spectra that causes a drop-off. It is due to pockets of neutral hydrogen scattered throughout the intergalactic medium, kind of eating away at that spectrum, creating that drop-off, and it's dependent on redshift, so we can use that to figure out what redshift the gamma ray burst is at. And so we simulated a whole bunch of Roman observations of gamma ray bursts and tried to see if we could retrieve the redshift. So that's kind of what that plot is over on the right, showing the input redshift and output redshift. I probably don't have time to go into everything going on in that plot, but I will say that it seems that the accuracy of redshift estimation with the high latitude time domain telescope is dependent on the GRB flux and how long between the GRB going off and its observation. But these limitations can help inform how we design future surveys with the Roman telescope for gamma ray bursts. So if you're interested in hearing more, come find me or check out my poster. It's poster number 7. Thank you all so much.
Oh, this one? Is this
Yes.
one? Yeah, okay.
All right. Hey, everyone. My name is Tony. Thank you very much. This will be a really quick one. I don't have a whole lot to show, but I just wanted to show you the work we've been doing. I'm about to be a 6th-year grad student at OSU, but I've been working for the last 2 years with Chris Arata, and this is the majority of the work that I've done for him is on the simulator called the High Atomic Z Astrophysics Radiation Dynamics Simulator, which is the name we've given it. The purpose for this was Jeffrey Kruk identified in 2016 that the space environment at L2 is quite hazardous. So you're looking at what, like 1,800 particles, or sorry, not necessarily particle events, high energy particle events per second. So some quick math with 3-second exposures, you got like what, 5,400 particle events, and if you're looking at like the deep field stuff, like 60-second exposures, you're well over 100,000 particle events. So one of the great things about Roman is that it has those small pixels we've all been gushing over, but because they are smaller pixels, we do expect a lot more cosmic ray contamination. But this is a great thing because it'll allow us to like resolve more of the structure and morphology of these things. So the whole point of this simulator was to elucidate that structure, morphology, and also to provide us a model for what actual flux to expect for cosmic rays throughout the year and throughout time. And this is my team that's been working on with me to develop the simulator. All right, please see me at poster number 10 if you have more questions. Thank you.
Right, hi everyone. My name is Honaker. I'm a graduate student from the University of Delaware working with John Gieses. I'm very interested in brown dwarfs in our solar neighborhood, and I'm really excited for what Roman's going to do to help expand and go to that, maybe the next neighborhood even. But one of the things I'm really working on right now is how do we take these early discoveries and brown dwarf candidates and start to characterize and classify them in early Roman data science. So to that end, I've been working with the Becker World's Planet 9 collaboration, which is a NASA citizen science project, where we have a sample of spectroscopic follow-up observations, about 250 that we then supplemented with about 500 more brown dwarf spectra. And we computed synthetic Roman colors for them, and we fit color spectral type relations for the young, field, and low metallicity objects in hopes that this can be one of our early diagnostic tools to help type these objects and eventually work towards distance classifiers. If this interests you, come see my poster number 11, come talk to me, or send me a message on Slack. Thank you.
Hi, my name is Lauren. I work with Trevor and Joel Zinn. One of the main things that I'm focusing on for my poster is working on a saturation pipeline for Roman. I know one of the main things that we've heard a lot is that red giants struggle a lot with saturating quickly, as well as the awesome number of pixels that we get to work with. So my whole thing is working on removing saturated pixels so that we can reach more within the saturated lines, working with red giants and such. And in doing so, in replacing those pixels and masking them out for L2 data, we're able to get recoverable flux information. So if you'd like to learn more about that, I am poster number 13.
Oh, this one's not yours. I'm sorry. Oh, hang on. Okay. Which one is yours? I'll just pull it up from here. Let me go back here. This one? Oh, that one's not yours? Even though I put your name on it. Okay, let me pull it up here. This one at the bottom is not yours? No. No, oh, okay. In that case, let's just find it here. Can you show me here which one it is? Is it this one?
Yep.
Okay, let's just put it right here. Okay.
Hi everyone, my name is Hussain and I am a second year grad student at Baylor. What we're doing at Baylor is we're simulating large samples of mock supernova data. And we are asking two questions. If we create mock supernovas using cosmology that allows for dark energy and dark matter to interact, the first question we're asking is, will Roman be able to see such interactions, especially that we will be able to observe supernovas at high redshifts? And if you look at these Hubble residual diagrams, especially at low redshift and high redshift, there are some bins which will help us to figure out if these deviations or these interactions are taking place. And the second more important question we're asking is, suppose there is a signal in Roman that we're seeing that such interactions can take place. What we're going to do is, what everyone does is we just push it through the standard WCDM, W0, WACDM analysis. And if we do that, you find that it does converge, but we do get a biased W and W0. So what's happening over here is that you have interacting models that are masquerading as evolving dark energy. So what we need moving on is new analysis in which we are able to differentiate between interacting models of dark energy and evolving models of dark energy. Yeah, and my poster number is 14. If you have any questions about these plots and these results, you can come and talk to me. Thank you.